Hello and welcome to this GCSE exam preparation video on the particle model of matter. The particle model uses circles to model the particles in a substance. The circles could represent atoms or molecules depending on the substance. In a solid, the particles are touching and in a regular pattern. This represents that the forces between the particles in a solid are strong, that the particles cannot move about, only vibrate around a fixed point, and that a solid cannot be compressed as the particles can't get any closer to one another. In a liquid, the particles are touching, but they are not in a regular pattern. This shows that the forces in a liquid are not as strong as a solid, so the particles in a liquid can move around, they can flow. That they are touching shows that a liquid cannot be compressed. Like a solid, they can't move closer to one another. Particles in a gas are very far apart, as the forces between the particles are the weakest here. Gas particles move around in random directions with a range of speeds. They are not all at the same speed. Also, gases can be compressed. This is shown in the model by the particles being far apart and that they can be moved closer together. The particle model also explains density. In the same volume container, a solid will have far more particles than a liquid. The least number of particles will be in a gas. So solids have the highest density, most of the time, followed by liquids, and gases have the lowest density. This is the equation for calculating density, and it is one that you have to learn. Density equals the mass divided by the volume. The units for mass are in kilograms, volume is in meters cubed, and density is kilograms per meter cubed. It's worth learning those units, particularly the ones for density, because they often come up as a bonus point in exams. For density questions, you might have to do some converting units. If you need to convert from grams to kilograms, because kilo means 1,000, then the factor of change is 1,000. You would need to divide by 1,000. To go from kilograms to grams, you need to times by 1,000. The conversions for volume are a little bit more complicated. If you think about a metre cubed, it's a metre by a metre by a metre. Or you could say it's 100 centimetres by 100 centimetres by 100 centimetres. If you work that out, you find that in a metre cubed there are 1 million cubic centimetres. So that's our factor of change. So to go from centimetres cubed to metres cubed, you need to divide by 1 million. And to go from metres cubed to centimetres cubed, you need to multiply by 1 million. To cause a substance to change state, you need to either heat it or cool it. You need to know the names of all the state changes in both the heating and the cooling direction. To go from a solid to a liquid, when you heat it, that's melting. Continue to heat it and it will boil or evaporate into a gas. And some substances, like dry ice, which is solid carbon dioxide, will sublimate, which means it goes straight from a solid to a gas without going through the liquid phase. In the cooling, this is removing energy from your substance. To go from a gas to a liquid, this is condensing. Freezing is when you go from a liquid back into a solid, and desublimating is when you go from a gas straight to a solid without going through the liquid phase. Changing state is a physical change. The substance remains the same, it's just in a different form. The process can be reversed, and the substance will regain the properties it had in the original state. Changing state also conserves mass. No particles are lost in the process, so the mass that you had at the beginning and the mass that you have at the end are the same. As energy is given to a substance, the temperature can be measured and then plotted against time. The graph plotted is called a heating curve. And when a substance is cooled, the temperature plotted against time is called a cooling curve. Temperature is a measure of the average kinetic energy of substance. There are different phases on these graphs. There are areas where the temperature is changing because the average kinetic energy of the particles is changing. And there are areas where the temperature is not changing. This is where there is a change in state. The energy change in the system is breaking or making the intermolecular bonds between the particles. At the points where the line is horizontal, the heating has not stopped. The energy is just doing something different. When the temperature is increasing, the energy is added to the kinetic store, and so the internal energy is increasing. When the line is flat, the energy is breaking bonds between the particles. The substance is changing state, but the energy is still going into the system, so the internal energy is still increasing. In a cooling curve, where the substance is reducing in temperature, energy is being removed from the kinetic store, so the internal energy decreases. When the line is flat, bonds between particles are being made. This gives out energy, so the internal energy is decreasing here as well. Where there is a change in temperature, you need to use the specific heat capacity equation. Where the line is flat, you need to use the specific latent heat equation. Energy stored inside a system by the particles in the system is called internal energy. Internal energy consists of the kinetic energy of the particles plus the potential energy of the particles. Heating changes the total energy of the system by increasing the energy stored in the system's particles. This can do the following. It can increase the temperature of the system, and it can cause a change in state. If there is a temperature change, the size of the change depends on the mass of the substance, the type of the substance, and the amount of energy transferred. This can be calculated using the following equation, which will be given on your datasheet. This is delta E, change in energy, equals m, mass, times the specific heat capacity, C, times the change in temperature, which is delta theta. The Greek symbol delta, capital delta, means change. So delta E is change in energy and delta theta is change in temperature. If there is a change in state, the energy required depends on the amount of mass of substance and the specific latent heat of that substance. The following equation can be used, and that is on the datasheet as well. E equals ml. Energy for a change in state equals the mass times the specific latent heat. Specific heat capacity appears twice in the syllabus. It's here and it's in energy stores and transfers. Both are paper 1 topics. The definition for specific heat capacity is the energy required to raise the temperature of 1 kilogram of a substance by 1 degree C. Water has a specific heat capacity of 4,200 joules per kilogram degrees C. This means it needs 4,200 joules of energy to increase the temperature of 1 kilogram of water from 20 to 21 degrees Celsius, an increase of 1 degree C. To calculate it, the formula is change in thermal energy, delta E, equals mass, m, times specific heat capacity, C, times the change in temperature, delta theta. And again, you don't need to remember this, it's on the datasheet. What is the energy required to raise the temperature of a 0.24 kilograms of water from 20 degrees Celsius to boiling? Well, first of all, let's have a look at the temperature change. 20 degrees Celsius to boiling is really 20 degrees Celsius to 100 degrees Celsius. So the change is 100 minus 20, which gives us 80. Then we need to substitute our numbers into the equation. So our mass is 0.24. Times by our specific heat capacity for water, which is 4,200, and times that by our change in temperature, which is 80. And this gives us a change in energy of 80,640 joules. Specific latent heat is the energy required to completely change the state of 1 kilogram of a substance. There are 2 different types of specific latent heat. There's the specific latent heat of fusion. This is the energy needed to change the state of 1 kilogram of solid to liquid. It's also the amount of energy removed from the system when you change 1 kilogram of liquid and freeze it into a solid. The specific latent heat of vaporization. This is the energy required to change 1 kilogram of liquid into a gas. It's also the amount of energy that is removed if 1 kilogram of gas is condensed into a liquid. The equation for specific latent heat is given on the datasheet, so you don't need to remember it. The equation is E equals ml. Energy for a change in state equals the mass times the specific latent heat. In the exam, you'll have to look at the information in the question and use either the specific latent heat of fusion or vaporization, depending on the circumstances of the question. The units, energy is in joules, mass is in kilograms, and specific latent heat is in joules per kilogram. And that's the end of the particle model of matter part 1. See you in part 2.